catch up to you guys here. So what's the first thing I should do? I like it. Put it in the right form so I can see how to graph each line quickly. So on the first one, if I add y subtract 2, should get there. Or you guys might have subtracted x divided by -1. I always like to avoid too many negatives. So if the y is negative, I add it. And then I just subtract the 2, and then I don't have to worry about remembering the negative stuff. Right? Well, the second one's easier. Just subtract the x. So that first guy, what's the y-intercept? Cool. 0, -2. And the slope tells me to do what? Up 1 over 1, up 1 over 1, up 1 over 1, down 1, back 1, down 1, back 1, down 1, back 1. Okay. So do several steps, just to make sure. And then here's my, let's see if I can do this. Can you do it, Jeff? I'm going to find out. That's pretty good for me.
Can you do that one more time? I'm not understanding how you're going over 1 over 1.
Oh, for this first guy, the y-intercept, 0, -2, right? Mm-hmm. And what's the slope for the first one? 1. Is that cool? So right here, what's the slope of that equation?
1 over 1.
Yeah, 1, and I put it over 1 just so I can see rise and run. So from any point, and of course I'm going to start at the only point I know, the y-intercept, I can go up 1 over 1, up 1 over 1. Now, this is the same as -1 over -1, which means I can go down 1, back 1, down 1, back 1. All right, let me stop there for a second. So everybody right now, especially because we just took a quiz on it, you should be able to do that. That's the quickest way to graph a line. And the second one, the y-intercept is? 0.6. And the slope tells me to go down 1 over 1, down over 1, down over 1, down over 1. Hey, all right. I lucked out there. Okay, guys, let me see if I can freehand this. Sure, man. So what's the answer?
4, 2.
Good, 4, 2. And how do you check that? Plug it in. It's crazy. So plug in 4. 4 minus 2 is 2. That's crazy. 4 plus 2 is 6. Awesome. Kick ass. So if you do not put this, you will lose a lot of points because the whole point of it is to find the answer. So if you do all this work and then don't tell me what the answer is, you miss the whole point. You got to get the answer. All right, maybe. It's not too bad, right? If you can graph lines, this is pretty simple. All right, so let's see. Try number 2 and 3. 3's got something weird. Some of you guys probably already did them. Just hang out for a second. Call me over if you need some help. Some of you guys got to be careful. I know some of you guys remember the algebraic way to solve these. Something called elimination and substitution. I don't want to see any of that shit here. This says solve graphically. Now, if on another sheet of paper you want to do it just to see what the answer is going to be, that's smart. Just so you know if something went wrong when you graph your lines, you know what the answer is supposed to be 3, 7, and you're getting 2, -8. You're like, shit, what did I do? Let me do number 2 real quick. Y-intercept there is going to be 0, -4 on the first guy. And the slope tells me to go how? Yeah, so this slope here tells me to go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Okay. Down 2 is off the graph, so hopefully they didn't give me too small of a graph. And then the line. Yeah. And the second dude, y-intercept is good, 0, 2. And the slope tells me to go how?
No.
Good. 1, 2, 3, 4 over 1. Hey, kick ass. Wobbly line. So what's the answer?
1, -2.
Yeah, 1, -2. That's the most important part. Get that bad boy, and then you can check it by plugging it in, and it does work. Thank God. So what's going on with number 3? Anybody got somewhere that?
Parallel line.
Yeah, freaking parallel. That's a little bit evil. Because if the answer is where the 2 lines meet, and the 2 lines are parallel, parallel lines don't meet. So what's the answer going to be? No solution. So if we graph this, -1 up 2, down 2 over 1, there's one line, and the other line is going to be 0, 2, down 2 over 1. It's going to be parallel. And there's not going to be an answer. So the answer is no solution. Do not circle your graph or something. It's like, ooh, it's a graph. No, the answer is there is no answer. I like it. And the one other weirdness, so you could have one answer if they meet. You could have no answers if they don't meet. There's actually a way to get an infinite number of answers if they actually are the same freaking line. So again, if the answer is where they meet, and they meet everywhere, then the answer is every point on the line. I like it. Why would it make no sense to say the answer is all real numbers? What does an answer look like in this kind of problem? What's an answer look like? A point. So it's not a real number, it's a point. It's a set of 2 real numbers, right? So the answer here won't be all real numbers. The answer here will be an infinite number of points. The answer's always got to be points. No, because that would be too specific. That would say they meet at infinity. When actually they meet everywhere. Yeah. I like it. Maybe. So let's see a little motivation as to why this is not good enough in general. If I actually had to solve this set of equations, yeah, dude, I like it. Do you want to solve that graphically? No. Can you find the pi intercept very easily? I can approximate it, but not perfect. So graphically will only work really when the answer is something like a whole number normally, or something really, or half maybe at the most. The minute it's off of there, we're not going to be able to find that intersection very easily. We're not going to be able to find it. Do you guys kind of follow? I'm trying to lead us into algebraic ways to do these problems. So graphically is only so good, because we're only human. We can't graph it perfectly, and the answer needs to be a whole number so I can really see it meet. If the answer is some weird little 7.837, I'm not going to see that. Oh yeah, 7.837. No, especially not the way I graph. All right, but even if you graph perfectly, you ain't going to get that answer from your graph. You're just not. We're human. So there must be an algebraic way to do this, and because the algebra doesn't care. The algebra can handle any freaky numbers you throw at it, right? So let's talk about one way to do that, and then we'll head out. So let's maybe not tackle that problem here quite yet. Let's start with something a little bit nicer. And actually, let's do this. Let's, yeah, Jeff, let's do this. Let's take something we already know the answer to. Number 2. So we got 2x minus y equals 4. y equals 2. Okay. So the way to solve a system of equations, they give you two lines that you say, okay, both of those lines are true. So the answer is going to be where both are true at the same time. So one way to do this, instead of graphically, is something called substitution. Substitution, okay. So there you know this method. So what would I do? How would I use substitution here? So you have to do one little thing to get it started. So here's the idea of substitution. How many variables are in each of these equations? 2. So it seems impossible on the face of it. I mean, graphically it kind of makes sense. I can find it. But algebraically, there's two things I don't know. Shit, there's no way to solve. If I try to solve, I get y equals x business. But here's what you do. If you took the second one, for example, solve for y. Why do I not want to solve for x? Because what would happen if I tried to solve for x? I would make what show up? Fractions, right? You only have to do that if they force you to do it. Y is better because there's no coefficient. I'm not going to make fractions, right? So, of course, we already did solve it for y. If we do this, we get y equals negative 4x plus 2. I really want this to make sense. So what does that equation say is true? Y is that. So look back at equation number 1, the other equation. It says 2x minus y, but what the hell is y? What is y? Negative 4x plus 2 equals 4. So I took the first equation, and in place of this, I put what y is. That's why we said, what are we going to call that situation where we substitute? Let's call it substitution, yeah. So this name makes sense. I substitute this in for y, because that's what the hell y is. And now, what's better about this equation? Yeah, there's only one variable in it. There's only x, right? So how do I solve this equation? Distribute, I like it. So distribute the negative. So I get 2x plus 4x minus 2. So I get 6x equals 6. X is 1. Now don't just circle that and go on, because your answer has to be a point. So it's got to have two parts to it, right? So if x is 1, what's y? No. It shouldn't matter which equation you plug it into. Why should it not matter? Because the answer I'm getting is going to work. What's the whole idea of this? I want to get where the two lines meet, which means the answer has to work in both. So it shouldn't matter which one I pick. So if I plug 1 back into this guy, what do I get? Negative 2. If I plug 1 into the other guy, right? Plug 1 in for x. I get 2 minus y equals 4. I get negative y equals 2. I get y is negative 2. I get the same freaking thing. Of course I do, because it's the same point that they're both talking about. So it doesn't matter which one you plug it back into. But if you plug it into both, it's a way to check your work. Make sure you get the same thing. So what is the answer? Kick ass. 1, negative 2. That is the answer. So if I did graph it, which we did, and thankfully we got the same answer. Right? I forgot to look at that. Thankfully we got the same answer. Anytime I solve a system of equations this way, if I did graph them, they would meet at that point. That's what that means. Kick ass. Kick ass. So what do you think the answer if you had two parallel lines? Let's try this one, and then we'll head out. So number 3, how do I do substitution on number 3?
Negative 2x minus 1 equals 10.
Yeah, I can solve for y, one of these. It doesn't matter which one. So if I take the first one and solve for y, I get y equals negative 2x minus 1. That kicks ass. Cool. Which we already did. And then what do I do with that? Substitute where? see the other equation. If you plug this back into itself, you'll get something that's always true. It's called circular logic. I am Jeff. Jeff is me. Yay, Jeff. That didn't tell me shit. Right. So if you plug it back into itself, it's like, oh, I work inside of me. Ooh, neat. Right? That's just weird. So make sure that you got to number your equations so you keep track of what the hell you're working with. I've got the first equation's information there. I've got to use it with the other piece of information to figure something out. So if I take the second equation and write it like 2x plus, what do I put here? Negative 2x minus 1, because that's what y is. Y is this. So I'm going to plug this here. Let me try to make sure you guys... So I'm just rewriting equation number 2. 2x plus y. Well, here's plus y, because y is that. That's what y is. Equals 2. And what do you get? What's 2x plus negative 2x?
Negative 1 equals 2.
Yeah, this is 0, so I get negative 1 equals 2, which we already know how to interpret that. That means there is no solution. Yeah, it's the same answer we got visually. Right? So algebra is just another way to solve this equation. And of course I'm going to use an algebraic method when there's no way I would graph it perfectly, like the problem I had over there. So algebra works all the time. Graphically only works sometimes if we're doing it by hand. If I did it in the graphing calculator that we don't need to have, it would work all the time because that's what it's supposed to do. That's why it costs so much money. It's supposed to graph perfectly. All right, that's plenty. So tomorrow I'll have these quizzes graded.